Yeah, so thanks to the organizers for the wonderful meeting and for the opportunity to be here in person and talk to people again, and tell you about this new direction of research in theoretical high energy physics, which is basically taking the tools and ideas and essentially the ambition that we heard from Lance and Nima to do all orders in QCD or n equals 8 or n equals 4 and apply it to calculating gravitational wave signals that's relevant directly to the gravitational wave science program. Okay, so I don't have much time. Let me just jump straight in. The discovery of LIGO in 2015 has put us on a trajectory towards third generation gravitational wave observatories, which hold the promise of detecting nearly every binary merger in the history of the universe, which is about 1 million detections per year, at a sensitivity far greater than those of current detectors. Okay, this means a lot of science potential, of course, but hinges crucially on complementary advancing the knowledge of modeling gravitational wave sources. Okay, and that's where our community with our tools come in. The reason the path from Einstein's equation to binary dynamics is so difficult is because of multiple scales that are nonlinearly coupled through general relativity. And those two complications, multiple scales and nonlinear couplings, are exactly the same features that drove waves of breakthroughs in gauge theories and led to tools like effective field theory and scattering amplitudes. And so naturally, these tools will fit in. If I had more time, I would tell you why observables in classical dynamics are naturally extractable from endpoint amplitudes, how classical compact binaries have essentially the same features as their quantum counterparts, and so on and so forth. But the main message here is that we can leverage the same engines that drive calculations in modern particle theory for gravitational wave science. Okay, and stealing from Lance, when we do that, we not only enable precision at future detectors, and including searches for new physics, we also uncover theoretical structures. And theoretical structures lead to new tools lead to a deeper understanding of phenomena, both in gravitational wave theory, but there's also would be a feedback towards amplitudes. Okay, so just to make sure it's clear, this program brings together the mathematical and physical tools of theoretical high energy physics and applies it for gravitational wave science. And there are three goals broadly defined. First is to produce state-of-the-art waveforms. Okay, that's what we need to make the measurements possible. Second is to develop the tools from theoretical high energy physics. Some of the tools fit right out of the box. Like I said, tools for quarkonia, a lot of that fit directly to binary and spirals. But some tools need to be tailored. And so there's also development that needs to be done. And finally, as I said, this is a very, very good opportunity to explore new structures. Some of these structures are obvious from particle physics or amplitudes, but are not manifest in binary in spiral processes. On the other hand, some of these theoretical structures are rooted in a classical limit and have yet to be explored through the lens of quantum field theory. So there's a really interesting opportunity here. Okay? And so this program is not only very theoretical high energy physics. In fact, I would say these three are the hallmarks of a potentially great problem in theoretical high energy physics. It is also very welcomed by the general relativity community. Okay? So in a paper here by Thibaut Damour, he is one of the leading figures in general relativity. He clearly invites us. He says, we urge amplitude experts to use their novel techniques to compute the two-loop scattering amplitude of scalar masses. Okay, this was late 2017. About a year later, we answered, and we gave the two-loop amplitude in the classical limit for two black holes scattering INT stars. So let me just tell you what this plot is. This plot was made by our friends at LIGO. These are Alessandra Bonanno and her collaborators at the AAI. And they are theory members of LIGO who are very interested in these calculations using TFT tools. And so here they make a plot, first of all, of the binding energy measured in units of the total mass of the binary as a function of orbits to merger. So there's 40 orbits to merger, 20, and so on, and then they coalesce right here. This solid line right here is numerical relativity together with a phenomenological model called EOB. And these two are the benchmark models for producing waveforms. And they were very interested in our results at tree level, 1 loop, 2 loop, and 3 loop. Some of the authors are here presently, Ira and Zvi. And they were interested to see how does it do. So they made a plot, and as you can see here, it gets better and better and goes closer to truth. There are two key takeaways. One is that they were very pleasantly surprised of how well these predictions did and really wanted more. But secondly, the other thing that they studied was how to incorporate these together with numerical relativity and EOB. So these predictions are not meant to replace numerical relativity, but to be taken together with numerical relativity and EOB to form very accurate waveforms. Here's another observable that they looked at, which is the scattering angle. So previously, this was a binding energy of a bound, two bound compact objects. A scattering angle describes the scattering angle for one black hole passing through and scattering off out at infinity. This is not something that LIGO is currently looking for, but this is something that they've done numerical relativity simulations of and could compare predictions. So as you can see again, there's very nice convergence towards numerical relativity. Okay. Just to give you a flavor of what goes into this, sorry, I didn't see that actually. Did you remind me? 3. Okay. Just to give you a flavor of what goes into these calculations. Again, it's using the same tools that Nima and Lance were talking about. We start with gluon scattering amplitudes, okay, and square that using the double copy to get graviton tree-level scattering amplitudes. We use on-shell methods to sew this together into cuts. And then finally, we use advanced multi-loop integration, so IBPs, differential equations, and so on, to integrate this and get the classical amplitude, also together with effective field theory techniques that really let us efficiently target the terms that we need. So we want to target classical dynamics in a particular regime. And also using effective field theory, we can then map it on to, for example, a potential that we could hand off to our LIGO friends. In particular, it really goes, it should really be acknowledged that a lot of the work, especially by Walter and Ira, paved the way for this kind of technology. Okay? And this is not just a new technique that replaces old techniques or whatever. It really is producing new results. So for example, in this plane, you see here, this is Newton's potential computed in the 1600s. These are corrections Einstein computed in this 1930, and so on and so forth. And this is the state of the art. This is where, sorry, it's a little faint here, but this is where we need to be, for example, to get accurate enough for waveforms for third generation detectors. And this is what the amplitudes approach has so far computed. So as you can see, it's not computing in these diagonals, which is basically set by the virial theorem, but it's doing what we do in particle physics, which is to compute in small coupling, all orders in velocity. Okay? And given that these are new results, there's of course not immediate acceptance by the community. It takes a while for them to really appreciate these results. 2 weeks after our result, people were already computed the V6 term here, but this V8 term took a while, and it had to do with this contribution from this graph, which in particle physics, we would actually understand very well because it's related to the cusp anomalous dimension and also the heavy anomalous dimension in HQT. But it took a while for people to really understand why this number in front here was the number, but eventually it was resolved, and by now there are multiple confirmations of this. We are currently in a similar situation where there's an interesting discussion about the number that's here at G to the 4, V to the 4, where 2 groups agree, but 2 other groups don't. And it has to do with so-called tail terms and memory terms. Okay, I don't have time to discuss that, but that's an interesting thing. So beyond the higher orders that I showed you, there are multiple directions that one can study here. I only talked about scalar black holes, so no spin, but of course real compact objects have spin. So there's lots of a big body of work studying spin and also tidal effects. So big compact objects have finite sizes and they're subject to tidal effects. In fact, that's one of the key goals of gravitational wave science, is to pin down the neutron-star equation of state through precision understanding of these tidal effects. There's also studies with radiation and studies not applying the double copy at the amplitudes level, but thinking of the double copy in terms of the classical solutions. Okay, so I apologize, I'm going through this very quickly here, but just to sample some of the ideas. As I said, as we do this calculation, we uncover theoretical structures. We, for example, identify which terms in the amplitudes correspond to all order solutions like Schwarzschild and Kerr and so on. And we could start to think of how to leverage those perhaps in order to even further the calculations at next order. And finally, there are new methods. I'd like to point out two. One is by a group here, purely made out of general relativists who were interested in our amplitudes result, jumped in and ended up with a very novel method. So they noticed some structure in the amplitude and said that this means that we could extract a lot of information from self-force. And that's what they did. And that's how they're pushing the state of the art right now. Another method that's really worth mentioning is this method called KMOC. It's by Kosover, maybe, and O'Connell. And it derives the classical limit of amplitudes very carefully, defining, for example, sort of in an event-shaped like way, what the observables are, what the states are, what the incoming and outgoing states are, and so on and so forth, okay? So this is a very carefully crafted framework and has now led to also very high order calculations, for example, that has been used to understand radiation. Okay, so my hope was just to introduce this field to you. And the other message is that it's very new and there's still a lot of open questions left. I think even we're just even starting to ask the right questions, like what exactly are the observables? When we talk to our GR friends, they speak in a different language, and we speak in a different language when we have to connect those. And sometimes it's not what they have in mind doesn't exactly make sense in terms of amplitude. So that's another open opportunity to really ask the question of how do amplitudes, scattering amplitudes, actually define these observables? Okay. And let me just end by leaving this timeline to remind you that this is an opportunity for our field, that we have the right tools to really make an impact on a very important science frontier. Okay? Thank you.
Thank you. Questions from Mikhail? Yep. Gary?
I mean, for applications to LIGO, we need the gravitational waveform. And when I heard earlier talks about this, people were focused on the conservative part of the potential and not radiation. And I noticed you said that the radiation is now beginning to be discussed, but I mean, I don't quite understand the quote success, and all of those orders of G and C were not for the radiation. Is that right?
That's correct. So here I was talking about just purely conservative, which happens to be the quantity that our LIGO friends want and they can process into waveforms. So when they do it, they need two quantities. One is describing the conservative dynamics, which could be, for example, a potential or a periastron advance in a conservative setting. And then the second one is describing the energy loss through fluxes. And they put these two things separately. Now, from an amplitude perspective, these things are not separable. When you compute an amplitude, unless you're exclusive, radiation happens, right? And so this is part of the things that I was referring to earlier, that we're now starting to understand that, for example, how do you exactly define conservative from an amplitude perspective? These are the kinds of questions that we're running up against now. But to start, just to get on the ground running, we wanted to really compute things that are directly in their language that they can use. But now that we're doing that, we're realizing that, hey, based on amplitudes, maybe we should be organizing the calculation differently, and so on and so forth. But of course, as you can imagine, it's hard to move a big ship and say, here are the things that we computed, use them. But if it's not usable for them, they're not going to use it. So there's these two directions.
Thank you. More questions? Ira?
Yeah, I just wanted, thanks, that was a nice talk. I just wanted to point out that in addition, on top of the previous question, that's also just another piece of the puzzle. So this piece of the puzzle, in addition to the radiation, there's also dissipative effects. So for instance, quasi-normal modes of the black hole get excited, the black hole mass increases, and those effects actually come in pretty low order compared to these. So if, in fact, at b to the fourth, they come in. And so this program is one crucial piece of the larger puzzle, but there are other things that we need to calculate in addition. But there are effective field theory techniques for calculating those as well. So that's under the way to complete the whole thing.
Okay, I think we have to move on. So thanks, Mikhail, again.